All right, so we're starting on 13.1 today, which is the ANOVA, one-way ANOVA. One-way ANOVA. Okay, now the interesting thing about the ANOVA test, ANOVA stands for the analysis of variance, which is kind of a strange name because we're not actually, well, in order to do, so it's the funny thing is because it's a test of three or more means. So even though it's got variance in the name, the reason why it has variance in the name is because when you're testing three or more means, you have to figure out what the variance is doing. Okay? All right. So let's talk a little bit about the requirements. Okay? Number one, you're going to have k random samples, where k is at least 3. Okay? Of these k samples, they are all independent. They are also normally distributed. And we're also assuming that the populations have the same variance. Now, we have to define what does same variance mean. Same variance means the largest standard deviation is less than or equal to 2 times the smallest. Or in terms of variance, less than or equal to 4 times the variance. Okay? So the interesting thing about this, remember I did tell you guys earlier in the semester, sometimes we do standard deviation, sometimes we do variance. This is a case where we actually care more about the variance. Okay? All right, so let's go ahead, open up Canvas. And, oh, come on. I swear, it always makes me log in twice. I don't know why it does that. Really 3 times with this stupid thing. All right, so we're going to go to assignments. And in class worksheets, I'm going to go to the bottom, and we're going to do the worksheet 13.1 correct. Okay? All right, so in the book, they refer to these as X1, X2, X3, X4, X5, X6. I thought that was a silly name, so I renamed them with cities in Utah. But this basically is very similar with what the book has. All right, okay, so I've got between sample variation, Provo, Salt Lake, and Ogden. Okay? So the idea here is we want to compare these 3 means here. So in Provo, we've got a mean of 5. In Salt Lake, we've got a mean of 8. In Ogden, we've got a mean of 11. Okay? So the idea here is we're looking at our standard deviation. So we're assuming these are normally distributed, which may or may not be true, but we're hoping that they come from a normal population. You can see that the smallest standard deviation is 1. The largest standard deviation is 1.22. So as we look at this, so let's go through the requirements. I've got k random samples. Now this is just fake data. So we've got 3 samples in this case, Provo, Salt Lake, Ogden. We're assuming that these are all independent of each other. We're assuming that they're normally distributed. I probably should do a QQ plot to verify. And we're saying the populations have the same variance, which means 2 times the smallest, 2 times 1 is 2, is less than or equal to, let's see, the largest is less than or equal to 2 times the smallest. So if I take the largest sample standard deviation, 1.22, that's less than or equal to 2 times 1, which is 2. Okay, so we're assuming that in this case they have the same variance. Now, I've created some box and whisker diagrams here. Okay, so you can see here visually, actually there's hardly any whiskers on these because there's kind of goofy data. But you can see clearly these boxes don't overlap at all. Okay, so there's it's probably pretty easy to say, well, it looks to me like the mean of Provo is different from the mean of Salt Lake, which is different from the mean of Ogden. Okay, so this is what we're going to call between sample variation. These 3 don't overlap at all. Does that make sense visually? All right, so let's do another case where we've got Logan, St. George, and Orem. Okay, now we've got 3 others here. Okay, once again, I have the exact same 3 means here, 5, 8, and 11. Okay, you can see that the variation is much higher than the first 3 examples. But if I take the smallest here, which happens to be St. George, if I double that, 4.69 times 2 is roughly 9. The largest is Logan, 5 is less than 9. So we're assuming that these populations also have the same variance. We're assuming they're normally distributed. There's k independent samples. And in this case, we've got 3. So the interesting thing here is basically I have the exact same 3 means here and here. But as you can see visually, these 3 cities overlap quite a bit. It's much harder to tell because there's so much more variance in this case whether these 3 are significantly different. Whereas these clearly, because they don't overlap, clearly you can see it shouldn't be surprising. These 3 would be statistically significantly different, but much harder to tell with these 3 cities. Does that make sense? Because there's just so much more variation going on. Okay? And so the idea here is with an ANOVA test, in order to determine if these are different, we can't just simply look at the means. We've got to look at the variances as well. Okay? And that's why we call it an analysis of variance, because you simply can't just look at the means. You've got to also look at the variance. Does that make sense? Okay. So
Logan, St. George, and Orem, we wouldn't be able to use.
Well, it's not that we can't use them. It's just a lot harder to tell if those are significantly different. These are really easy to see they're different. Maybe they are, maybe they're not. I don't know. Okay, and so that leads us to. I wanted to kind of give you a big picture of why we care so much about the variance in this case. Because the means are exactly the same, but it's because of the variance that it's a lot harder to tell with the last 3 cities than the first 3 cities. And so this is kind of visual representation. Okay? All right. So let's bring up some terms. Okay? All right. So this one, you're going to be really glad I didn't put this on the last test, because this is very computationally intensive. Okay, so let's bring up some terms that we're going to have to use. One of them is called the SSE. Okay, the SSE stands for the sum of squares due to error. Okay, and the SSE, the formula for that is n1 minus 1 times s1 squared plus n2 minus 1 times s2 squared plus as many samples as you have. Okay, so you just keep going until you get to the end. Okay, so that's the first one. The second one we're going to do is called the SST, which equals the sum of squares due to treatment. Okay? The formula for the SST equals N1 times X1 bar minus X bar squared plus N2 times X2 bar minus X bar squared plus as many samples as you have. Okay? Then we have what's called the MSE, which stands for the mean square due to error. Okay? The MSE equals the SSE that you found previously divided by N minus K. Okay? In this case, N equals your total sample size, and K equals your number of samples. Then we have the MST, which equals the mean square due to error.
Is that the same thing as MSE?
Oh, sorry. This one's due to treatment.
So MSE is for treatment, MST is for error.
Would be opposite.
No, it's the opposite of what I said. I'll make sure I'm doing this right. Yes, this one's error. This one's treatment. Okay? Sorry about that. Okay, so the MST equals the SST divided by K minus 1. Okay? And then finally, the ANOVA test is an F test, which is the MST divided by the MSE. Okay? And in this case, your degrees of freedom equals K minus 1, comma, N minus K. So just as a reminder, F distribution, two chi-square distributions. We've got two sets of degrees of freedom, the numerator and the denominator, essentially. Okay? So, all right, let's talk a little bit about the steps to solve this.
So is the K minus 1 the numerator?
The K minus 1 is the numerator because your MST is in the numerator. Yes, that's correct.
And so if you want to find the up and the reverse, you just switch it. Or if you want to find left out.
Yeah, you know what, we're not going to use that stupid chart anymore. We're done with that chart. Okay, just remember this. Now, having said that, all of this is on your formula sheet except for your degrees of freedom. So put a little star by that. That one you're going to have to memorize. Okay? All the rest of that's on your formula sheet, so you don't need to memorize that. But you should be very familiar with how to do this. Really super good possibility that tomorrow's quiz is going to be on Excel. Okay? All right, so let's talk about the steps to compute. Okay? Number one, compute the combined mean, and we're going to call that X bar. Okay? The mean of all your data together combined. And then two, compute sample means, X1 bar, X2 bar, etc. Number three, compute the sample variances. So S1 squared, S2 squared, etc. For as many samples as you have. Step number 4, compute the SSE and the SST. And then finally, compute the F statistic, which is the MST divided by the MSE. Okay? All right, so let's go back to our data. Okay? And we're going to go through our 7 steps. Okay? We're going to use this data here. So the first thing we're going to do is we're going to look at Provo, Salt Lake, and Ogden. Looking at our box and whisker plot, you can see that we probably think those are going to be statistically significantly different, right? Okay? So let's look at this. So I've got my small sample variance here. So I just copied the data from Provo, Salt Lake, and Ogden. I got the means of 5, 8, and 11. Now, the one thing that I didn't do was the combined X bar. Okay? So if I take the combined X bar for all of this data, okay, that works out to be 8. Okay? So that's step 1. Okay? So find the combined X bar, I got 8. Now I need to find X1 bar, X2 bar, X3 bar, which I've already previously found 5, 8, and 11.
So for the SST, the normal X bar, is that what the combined X bar is? Is that the number we're using?
So the SST, we haven't gotten that. Let's see, SST, yeah. So we haven't gotten there yet. Okay, I'm just going here. So now we're going to compute the sample variances. So the sample variances, if I square each one of those standard deviations, so 1 squared is 1, 1 squared is 1, 1.22 squared is 1.5. Okay. Now we're going to do, and I don't know why I have the SSE. I probably should have done the SST first, but I'm going to do the mean square error. Okay. So the mean square error is the SSE, which is going to be N1 minus 1. Okay, so my N1 in this case, the N for Provo is 5. 5 minus 1 is 4. I'm going to take 4. I'm going to multiply that by S1 squared. So 4, sample size of 4 times 1 is 4. Okay? 4 times 1 is 4. 4 times 1.5 is 6. So that's the SSE. Does that make sense? Now, in this case, I'm going to take the SSE. 4 plus 4 is 8 plus 6 is 14. I'm going to take the sum of those 3 here. 14 divided by n minus k. Now my n in this case, I've got 5 times 3 is 15, right? 15 data points. I've got 3 samples. 15 minus 3 is 12. So I'm going to take this sum here. This sum here, 14 divided by 12 equals 1.166. So that's actually my denominator. Okay. My numerator, find the MST. Okay. The MST is the SST. The SST is N1. So I've got 5 in my first data set. And then this is what you were asking me, Trevin. I'm going to take X1 bar minus X bar. So 5 minus 8 is 3. 3 squared is 9. 9 times 5 is 45. Okay? Now I'm going to do the same thing here. 8 minus 8 is 0. 0 squared is 0. Okay, and then 11 minus 3 is 11 minus 8 is 3. 3 squared is 9, and 9 times 5 is 45. Okay. Now with my SST, just to add those up. So I'm going to add up the 45, the 0, and 45, which is 90. I'm going to take that 90. I'm going to divide it by k minus 1. I've got 3 samples. 3 minus 1 is 2. 90 divided by 2 is 45. Okay? All right, so I'm taking my 45. I'm going to divide that by my n minus k. 45 divided by 1.1666 works out to be my F statistic, which is 38.57. Okay, so just as a reminder, Glenn's in the other class. Glenn loves pictures. He loves that extra credit here. So here's what's going on. Essentially what I've got is I've got an F distribution. Okay, I've got a value of 38 point whatever I said. What was it? 38.57. The p-value is this area to the right. Okay, my degrees of freedom are k minus 1 and minus k. So in this case, k is I've got 3 samples. 3 minus 1 is 2. N is 15 minus 3 samples is 12. So my degrees of freedom are 2, 12. Okay? Now, the ANOVA test is always, well, I didn't mention that. Let's talk about our null hypothesis. Okay. I'm so caught up in the math that we didn't go through our 7 steps. Okay? In fact, even though we've calculated all this, let's go through our 7 steps.